Please get down to our homework tonight is 94 to 99. Still in chapter 2, so section 232. Then a little birdie named Mr. Mendrink told me that we might want to review a couple things from 231, especially when it comes to like angle-angle similarity. Yes. So please direct me towards which questions we should review again. Properties we need to go over. Here, I'll bring this down onto this screen. So 68. Do you think triangles must be similar if all three pairs of corresponding angles are congruent? Did we get through 68 dealing with if my angles are congruent?
I think we got through all the questions so we can really understand
Well, okay, so that's my real question then is not did we get through, did we understand? So, one issue that we can see, and Ava and I were just talking about this, is when these angles are rounding to the nearest degree, that's not 100% true, right? At some point, it's going to be less than 30 and bigger than 29, but it's not showing us that, right? So when you work with these tools, you have to be careful that you will be able to see situations where the angles are being rounded, and if you have corresponding sides showing, the side across from this 47 and that 47, if I can manipulate these triangles separately, now these are tied together through a certain rule, but if I can manipulate them separately, I might just get a little bit of a trig difference where it doesn't show my degrees off, but it is making one side bigger than the other. Like we always say, you can only trust technology so much. If you know congruent angles should produce proportional sides, and you get an answer that's slightly off, you know something in the technology's off. Probably it's rounded. So, about angle-angle similarity. Can anyone explain to me what that is saying? So our rule or postulate or whatever, we write like A, hello? Okay. Maybe. We write AA squiggly. And that squiggly means similarity. So when we talk about angle-angle similarity, we write, maybe? No. All right, who screwed with my smart board? It's not picking up anything. Well, sorry, Dilation dude. You're going to have to move. Who take these bottom corners down? Holy cow.
What?
Whoever take these bottom corners down did way too good of a job. Whoa. I didn't rip him.
Well, you ripped paper. You're ripping.
Dude, who's ever going to do that?
Well, I'm not ever.
You're so fucking.
Alright, so angle-angle similarity. So let's write in our notes AA with a squiggly. So let's talk about the most famous right triangle. What's the most famous right triangle? Okay, depends on if we're talking about angles or sides.
Oh, this one. I don't know.
If we talk about lengths.
I saw some flash.
Yeah, the 3, 4, 5.
Oh, okay.
Oh, that's.
So when talking about the Pythagorean theorem and trying to justify or prove or whatever to somebody using the 3, 4, 5, is the lowest integer side lengths we can use that work nicely with the Pythagorean theorem. Let's say we decide to blow that up. Because, blowing stuff up is fun. And we make it 6, 8, 10. Now we know our right angle has still been preserved. Now, if we know this is the most famous right triangle based off side lengths, but we're talking about angle-angle similarity, we're going to need to solve a couple angles. I'm going to introduce you guys to a tiny bit of trig here. This is why I'm asking you to have paper out, take notes. If I want to solve for this angle that we are going to call theta, looks like an Easter egg. We often use the Greek letter theta when working in geometry. It's a circle with a squiggly across the middle. Mr. Time. I can see that you're writing nothing down. Please get with us. You are. Come on. In order to figure out theta, we know two things. Well, kind of two things. We know how far of an opening it creates and how far away that opening is from it. Obviously, if the opening was closer to it, it would be a smaller opening. So think about your arms, right? The gap you can make with your arms will stay the same, but extend your arms out twice as long. The gap I've made at my body is the same, but the distance between my hands will get bigger as my arms get longer. So we use trig. Okay, trig is amazing. It's fantastical. There are 3 trig functions: sine, cosine, tangent. Now, there are actually 6 because we can inverse those functions as well, but there are 3 main functions. Now, something you may have heard. Throw it in your notes just as a brief taste. Sohcahtoa.
Yeah, let's talk about that.
We think about what are the corresponding sides that I have related to my angle. Now, here we have all of them. I'll tell you the easiest normally to work with is ignore hypotenuse. Don't know why. Just normally, if you have like sides to choose from, easier to go opposite adjacent. Just because they're straight sides. I mean, you can do whatever you want, but I'm going to use tangent. Now, what this saying, Sohcahtoa, actually means, Toa stands for the tangent of the angle will be equal to the ratio of opposite over adjacent. The question is the ratio of 3 to 4 the same as the ratio of 6 to 8? Then it makes absolutely no difference how big we blow the triangle up to. That angle will be the same. How we solve it? Now, you don't need to know any of this yet. I'm just giving it to you as like a little taste. Well, how do you get theta by itself then?
Use the calculator.
We already know this.
No, we already know we did. We gave us worksheets.
Hold on, I bet I can get you to it. If you had, I'm coming to you, Colin. If you had 3x equals 15, what's happening to the x? It is being multiplied. What do we do to get it by itself? Why? How do multiplication and division relate to each other? Well, inverse, right?
Dividing is just multiplying by a fraction.
Yes, I mean, they're the inverse of each other, right? Dividing is inverse of multiplication and vice versa. The inverse of tangent is the inverse tangent.
Yeah. Oh yeah, let's the next day.
Has its own. No. So to undo this, just like you can't not make the multiplication happen, but you can divide and make it like it does nothing. You just apply the inverse tangent to the whole thing. But if you're gonna do it on the left side, you gotta do it on the right side. So really, theta becomes the inverse tangent of opposite over adjacent, which we see here, 3 over 4. So on your calculator, you hit second tangent. I can give you a working pencil, if that's your issue. It's working, just it's in pieces laying on my desk.
Alright, wait.
It's not working very well to take notes right now. is all that I'm going to say.
Oh, is that the fraction addition thing again?
Yeah, so it was just inverse tangent. It was tan with the power of -1,
Okay.
which is your inverse tangent. So it is like dividing a multiplication. You're just doing an operation to undo the operation that already happened. You can't actually undo it. So a lot of things we say in math aren't actually what we say. It's just like what we mean. How do I get rid of multiplication? Well, you're not really getting rid of. You're dividing to compensate that after I multiply. If I divide, I can get back to where I want to. Like, it's this whole thing. So, in solving trig, anyone figure that out, what the angle size actually is there? Oh, come on, you can use even the TI-30s.
Yeah, 1030s aren't as good as the nice ones.
But here it does the exact same thing. It's actually just as easy. So, second the tan button, if you're going to play along with us. And then 3/4. 36, approximately 0.9. 36.8, yeah, about 30. You did inverse tangent of 3 divided by 4? Oh, you're in the wrong setting. So we'll get there later, but you're in radians as opposed to degrees. Don't worry about it. We don't need to get that far
So what
yet.
should I do then to change that?
You go into your settings. So you go into like menu.
I'll figure that out later.
Yeah, we can deal with that later.
If it gets-
All we're trying to get to is if I do the same thing, even having my calculator do it, this will be exactly the same. Because this fraction that I have plugged in here could be reduced from any larger value of side lengths. How the math works is with the simplified form of the fraction. Really, you could plug in a decimal there. We don't. We like to look at the sides separately. But any multiplication of that size will reduce back to the same ratio. Cool. This is why angle only produces similarity, because when we see, oh yeah, the angles are congruent, it proves they have the same ratio. It doesn't prove anything about congruence, but that same ratio proves similarity. Questions?
No.
70.
I think this is the one we were having trouble on.
So create a triangle with side lengths 4, 5, and an angle of 20 degrees between them. What'd you guys end up saying about this one then? Sorry, I wasn't here, so my apologies.
Oh dear. Let's not. It's impossible.
Oh.
I don't think it would be possible for it. Well, it should, basically it should be similar every time. Because if you're going because if you change the angles, the two unmarked angles, or like, then it's going to change the side lengths.
Okay, and likewise if we change the side lengths, well, not necessarily. So that rule does work one way, not necessarily the other. Because I could double my triangle, right, and the angles would stay the same, so I've changed the side lengths.
Well,
And I didn't change the angles.
but if you're going to change the side lengths in like proportion, as in like keep those two side lengths given and then change that one, it's going to change the angle.
Did anyone play with this? The E tool here?
For a little bit.
Not really.
So we have side lengths 4 and 5. Right, so we need to make side lengths of 4 and 5 and an included angle of 20. Right, I want to move this whole triangle. So 5. If I do it like theirs. So we make that happen. By the way, once you get something how you want it, This is not the same as it used to be. Sorry, they ran some updates.
Oh,
You used to be able to lock this. Unless just in this one, it's not going to. Yeah, it's an included of 20. So like that. So what they're asking, right, 5 on bottom, 4 included 20. Could we make 8, 10, or some kind of proportional that is not necessarily similar? So here's 10. Maybe. Change your angle. If it won't go, you gotta change your angle. And what, they wanted this to be 8. So now this is showing 19 degrees, right? Which isn't quite true, because this I could move to a different point and get it. So this is what we were talking about by the rounding. That was rounding down to 19 and rounding 8 up to 18 or vice versa, something like that. That's why it was goofing up, because it's not showing hundredths places or anything else, and this is not showing tenths places. So be careful. What if they won't show this length, will they? What if this was my side that was 8? Did it say anything about location of sides?
No.
Now up here, it does. Angle of 20 degrees between those two sides, right? In the secondary descriptions with the sides of 8 and 10, it doesn't say anything about where those sides would be relative to the angle.
Well, let's give an example of the like proportional side length. You think it would be assuming that you would keep the angle like between the two.
We cannot assume though. So one thing to point out is for this to potentially work, we got to talk about location, right? Order of our objects. What conclusion did you come to? Did you come to a conclusion? So they're really just referencing side-side similarity. I really wish my smart board was working today. I'm trying to turn smart on and see if that helps. It turned itself off. I don't know what happened. Well, I'm going to try to reboot my whole computer with you guys not here. So we know angle-angle similarity, right? We could go through, we could prove it. What we're asking ourselves is side-side similarity a thing?
No.
So angle-angle similarity says angles have to be congruent, right? Side-side similarity would just say they have to be proportional. So if you have two different sides proportional to two other sides, could we say those triangles must be similar?
What if the other two sides are different?
Different what?
Like the last, like the third side. Let's say like not proportional.
So we have a 3, a 4, and then a 5 over there, right? And then also we have like a 6, 8, 10, a manipulation, dilation. Well, here's a 3, 4. Right? I mean, I could create a 6, 8 with a 120 angle. But would it have to have a 120 angle?
Yes.
Not if I don't know anything about the third side. Right now, my third side doesn't matter at all. All I know is my 3, 4. So if you started relating a side-side, some kind of side-side similarity statement, I keep thinking I'm going to be able to write. If we think about side-side similarity like we think about angle-angle, the only thing it would be saying, and all of this is like hypothetical right now, is if two sides are similar to, like in proportion, if their ratios are equal, then we have similar triangles. So a 3, 4, let's just take a 6, 8, right? Double it up. Well, I see there, I can make a 6, 8 triangle that is not a 120 angle. It's a 90-degree angle. And I could actually bring that 6 towards the 8, all the way to my third side being just over 2. Or it could not be 2. Triangle inequality theorem. Because then 6 plus 2 would only equal 8. It has to be more than 8. But my third side there, because it's not part of it, this cannot work. So side-side similarity wouldn't work. But what about side-side-side? So we'll leave it with that for the moment. What if we had SSS? Similarity. Any other big questions that stuck out from the lesson? So this should have led you to that. Hopefully you guys talked about this last week. So he's really a science teacher. It's okay. I really just left it as let the kids work. I mean, I wrote him a little bit more notes than that, but I trusted that you guys would at least like absorb yourself in it and try these things. It's a little bit tough. So here we go. Triangle 1, triangle 2. So we have 3, 5, 7, and 6, 10, 14. What do we think? Make a prediction. What if we didn't know anything about the sides on the right, the angles on those triangles I drew over there? The 3, 4, 5, let's say you didn't know it was a right angle. You didn't know anything about the angles. And then I draw you a 6, 8, 10. What would you think? Like just immediately. If I drew you... Well, okay, that's a really mathy word. Let's go simpler.
The sides are corresponding. They're similar. Well, not that way.
Not
Like,
mathy.
If you showed it to like Math 7, Math 8 kid, what do you think they would think about with that 6, 8, 10 compared to the 3, 4, 5?
oh, you
Bigger.
multiply them by 2.
Oh, it's double,
Double.
right? Your brain would immediately, or half, right? You'd go to one or the other. You'd say double or half. So then, what if you asked them about the angle size? So, okay, so how do the angles on this triangle compare to the angles on that one?
Both are double. But
And why wouldn't that make sense?
because you see all
right.
the angles out of 180.
Ooh, so then we know it breaks a triangle rule. So we back up and we explain to them what? Somebody raise your hand and explain to me how we would tell them that that's not true. Doubling side lengths doesn't double angles.
So the rule that the triangle angle sum theorem, I believe, it says all angles in a triangle must add to 180. If you were doubling the angles in the first triangle, the angle, and for the second triangle to have angles adding up to 180, then the first triangle would have angles adding up to 90.
Ooh, so even the first triangle would have been broken. I like that.
Or
Chris?
Just
Hold on.
demonstrate a triangle that would have doubled lengths to prove that it cannot be done.
Man, I really wish I could draw. What about, so like we're talking to this younger person about these triangles, right? And we're trying to argue with them that this angle right here is the same as that angle right there. You keep talking in circles, they keep not getting it, and you're like, okay, fine. What argument do they have left? Like, they're trying to tell you the angles aren't the same size, but if I can show you that that one triangle lives inside of the other one because I can just draw a line, the length of these, just like I was saying with my arms, the length of the sides is irrelevant to how wide they open. I could also extend this and extend this. Now, the only rule that we would have to follow is we have to be parallel to this side because we can't go changing other things. But actually, even if we change other things, like this, and say that connects, is this angle still the same size? Yeah. But now we wouldn't have side-side-side similarity. If we change this one, we'd only have side-side, and again, that would fall apart. Because we can have the side-side and it not be similar triangles. So compose one triangle inside the other. That's kind of what we've been doing with the sketch or tracing paper. seeing that a lot of times if I can show one triangle inside or on top of or related to or up against, adjacent, things like that. So 3, 4, 5 to 6, 8, 10, we've pretty much already covered that. So how then? So you guys didn't really talk about 273? All right, I would like you to talk with your teams then, because if you guys just breezed over some stuff, and this might modify how our weeks look, how our week looks. So Robel's team is using the side angle side similarity and side 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 similarity conditions to show two triangles are similar. That is too much work, Robel says. Hey gentlemen, stop talking while I'm talking, or leave my classroom. Sorry. I don't talk when you're talking and give an explanation because I respect you. If you won't even give me that, then get out of here. If you don't want to learn, I'm not going to force you. So when using angle-angle similarity condition, we only need to look at two pairs of corresponding parts. Well, okay, so let's back up and check if Robel makes any sense. Because then he goes on to say, let's just calculate the ratios for two pairs of corresponding sides, determine if that's similar. But so let's check that statement about angle, angle. Why, for angle, angle similarity, do we only compare two parts? Take like 30 seconds to a minute. Make sure everybody at your group knows. If not, we'll address it. But see if everybody at your group knows.
Yeah. Okay, slow down. Okay, one of you guys talk. You're not going to talk at the same time.
I'm talking for
Youngest to so all agree it's everything. Yes. We're good now.
He is such a whiny person. I mean, 14-year-old.
She's not me.
I mean, almost 14. It's definitely
All right. Ryan, what do you think? I heard you talking about a lot of A's over there. Why do we only compare two?
Oh, because you can add, subtract it from the negative.
So when we know two, we actually know all three. And we use, if we were writing a proof, what do we use for that? Triangle angle sum theorem. Now, so Robel says, well guys, just in the same way, we can just compare two sides. So, as a group, does that work? If so, why? If not, why? So talk with each other. See if you guys all think the same thing. I don't know if what you're saying makes sense. Remember, he's comparing two sides. So he's saying, I do have two sides within ratio of each other. Now they do have an angle. They were trying to use side angle side, but Ro was lazy and he's trying to say, like, dudes, let's just compare two sides, we'll be fine.
But if you don't do everybody's angle, then you basically allow the people to change by the side.
I don't know. What? We talked to Colin a bunch. Somebody from this group. What do you think? What's your immediate gut response to Robel?
Don't.
Chill. You, Jenny, Owen, somebody.
Okay. So we got that. You could kind of get like a general idea of what the third one would be, but you wouldn't get. Because I don't remember what it was exactly called, but it's like kind of like equality, where it's B plus B is greater than C, like C plus B is greater than A.
Ooh. So hold on.
Like
So
a range of numbers, you couldn't get the specific number needed.
So you guys talked about the triangle angle sum theorem lets us for sure 100% we know it calculate that third angle. So likewise, Owen's trying to bring in what we know about the third side of a triangle. What do we know about the third side? We need to write this down. how it would fix itself. You can just clear them off your desk. You have a trash can right there. What do we know? Let's say we have that 3, 4. So, if we have sides that are 3 and 4 and something.
X.
Right, but what about that third side?
There'd be like a range, like it'd be an inequality, like it has to be in between these numbers.
Okay, how do we figure out the in-between? So let's go ahead and call this X then, I guess, just so we're not just using a question mark. We'll change groups. Ava?
So to find the lowest value, you add wait, crap. I know how to do it, but wait,
There's a super easy way, and the biggest thing is make sure these don't have or equal. This is how you make this easy. Make sure they don't have or equal.
If you add 3 and 4 together and then add 1, that is the lowest value. No, it's not high.
What? Start over.
Add 3 and 4.
Okay.
Yeah, that then subtract 1.
I agree, but I think you're saying them together, meaning them two separate things. Here's how we figure out our third side.
I can't talk too much.
That's it. Your third side must be bigger than the difference and smaller than the sum. Think about it, guys. This is where playing with Desmos is like, oh! Because if we took a line, or actually Desmos is great, but GeoGebra is also really good. GeoGebra is another, we'll use it this year. I just didn't want to overwhelm you guys right at the beginning.
Is that like algebra?
Geometry and algebra, you see the word combination.
Yeah.
Oh, I don't want graphing calculator. Sorry.
That's pretty close. This looks like Desmos.
There's a lot like that.
So, check it out. Well, Desmos kind of copied. So, if I have a, I want segment. I have a 3 and a 4, right? My third side, it's fixed. Unlock. I haven't used this in a while. It's in the properties.
No, it's not quite a 5. No.
I know, because now I need to fix the length. Alright, we'll get into this as we need to. I'm taking way too long to review a lesson from last week. We could rotate this up this direction all the way till it almost makes a line. But if we make a line, we no longer make a triangle. Like here, that would be bad. But if I make it go here, then I can still make a triangle. And my third side is almost 7. It's not quite 7. Now, if I swing it this way, then I would be connected to A out almost 4. Oh, there we go. And my third side right there is just over 1. And it will tell you everything and anything. GeoGebra's fun. Play with it if you want. So, I don't even know where we were. Where are we? That is why that falls apart. So, triangle, side inequality, or whatever you want to call it, is just some difference. Now, don't think of them as max and min, unless in your head you can remember they're not allowed. You can think of it as like max length, min length, but I can't use them. My max length would be 7, but I can't use it. My min length would be 1, but I can't use it. So you could have a length of 1.0000000000001. Your triangle is going to look like a straight line, but it's not.
That's not. Even for this, with another thing, even if we only had angle measures that were integers, then with just 2 sides, you have anywhere from 178 different areas
Mhm.
But what about 1.5?
Even if we all, I said even if we only use integers for angle measures.
Which is what this is. This will only use the integers. So we know this is invalid. Also, it's a bad word.
Well, you can flip it around, so.
Ah.
No, that is so too hard.
All right, and moving on. Let's check through 75. So take a moment because I wasn't here and I'm afraid that not much learning happened. Check through A, B, C, D. Make your own determination. Are these similar?
Wait, are we doing this now?
Yeah, because I want to review. We're just not going to do a new lesson. So this is going to be tomorrow's homework. So in your plan book, you're going to move it to the next day. We'll,
Wait, we have no homework today?
well, we didn't get to a new lesson. This is what you guys did last week.
Oh,
So,
that's true. Dang it.
I mean, if you want to do the next homework, you can.
And I might do it if we're done with all this.
I mean, it might because I have nothing to do tonight. And, you know,
I have lots of stuff to do.
no, I mean, organized.
Nothing.
What it was on Thursday. So shift today's to tomorrow, and today is just make sure you're caught up. By the way, I meant to do this with chapter 1, but chapter 1's so low key, I didn't want to stress people out. I collect the homework before you're allowed to take the test, so if you don't have homework done, you just don't take the test. So it's not like a gotcha thing, it's just like if you haven't done your practice, you're not ready to show mastery. So,
It makes sense.
take 2 or 3 minutes, we'll review this together before you guys get out of here.
Wait, so for all of these, can't we just say dilation and reflection?
I mean,
So if they're similar, so that's saying some of them might not be. Then describe the sequence. So some will need a reflection where others would not. Some would need a rotation instead because they line up, but just one is a different orientation. Like, could anybody give me these specifics for C? Is it similar? How would we go? And like as we get deeper and deeper, we want to get more and more detailed. So you can't just say dilation. If you can say more. C, we can say more for. I can't tell either of you. If you actually want to answer, you can. You just both put your hand up and down. Dilation from point M. And then, if we had a tick mark here and here, we could say dilation from point M with scale factor 2. Because then if we know that this entire length is double, if these are congruent, then it's double. What about A? Let's jump group. Somebody from Gunner's group. Are the triangles in A similar? Yeah, how would we get there? I mean, it's just your group, whoever wants to answer it.
So we have one angle in common visible that is 32 degrees.
Mm-hmm.
But so the way I solved this is I took my calculator and I added 32 plus 96 plus 52.
What'd you get?
180 degrees.
Sweet, which means,
They are similar.
so P must be 96. So still, how would we transfer them then? What's our rigid motion? Or sorry, not rigid, but what's our composition of isometries?
Dilation, reflection, rotation.
This will need a reflection because X has to map to J, V to P,
Yep.
excuse me, and K to O. We will need to reflect it. You know, like knockout. B. Somebody from B's group. Oh, sorry, question.
So, like, what if you don't have enough information to
What do you mean?
like, I don't know, you had,
I mean, easy answer is they're not similar. If you can't prove it, they're not. But do you mean like one of these or what?
yeah, like,
How? What do you mean you don't have enough information?
oh wait, yes we do.
So the thing that might be throwing you off is we know NH is parallel to SL because this is a straight line, and lines that are straight or lines that look straight are assumed to be straight. So they're not going to put like a 1 degree kink or like a 179 degree kink. Like that would be evil. So since we assume that's a continuous line and these congruent angles are corresponding, that tells us these are parallel. From there, we could prove that these angles are corresponding and therefore congruent. This angle is identity because it is itself, or reflexive. And then we have angle, angle, angle. Or we could have done angle, angle once we found that. So, wait, another question.
Just a random question.
E is group. What about B?
Yeah,
No, because
they
the
are.
sides
They
aren't
are.
proportional.
They are. They're proportional by a scale. 3.2.
How do we figure out the scale?
By the smaller number by the bigger number.
Yeah, well, easier way is bigger number divided by smaller number because that's how you get like values bigger than 1. So if we take 64 divided by 20, we would get 3.2. And then try 44.8 divided by 14. If that gives you 3.2, you've got side-side similarity, which doesn't prove anything. But then you have the congruent angle in between them. Now, I do not like that they don't give you the little tick mark thing. I require that you show some kind of like a single tick or a double tick or a triple tick or a triangle. Like whatever symbol you place on the arc has to be congruent, showing this angle is congruent to that angle. They only aren't showing that because they're like, I don't know. But because their other angles that we don't know anything about aren't showing anything, we can assume since they showed something, that means congruence. Or, yeah, congruence.
Oh, wait. What? Can I do D?
Can you? It's a question of ability.
May I?
Sure, real quick. What about D?
They're not similar.
Not similar, how do you
Sides
figure?
are not proportional.
So if we set up smallest sides to each other, we'd have 90 divided by 18.
That's 5.
What?
Yep.
Yeah, oh, sorry. I thought you were saying like that's 5. Sorry, I got stuck. So 202 divided by 44?
Not 5.
Or you just know that 44 times 5
It's not
would be 220, which is not this. Sometimes they'll trick you though. This side would have been 220. And sometimes actually what they've done can't even make a triangle. They just like throw labels in there. So the trick would be they'd make this 220, you'd see, oh, it works, and then you'd stop checking. Don't fall in the trap. Check all 3 pieces. Then this one, I forget if this one works or not.
No, it's like
5
it's
is
like
250. Oh, it's way off.
Yeah.
Because 5 times this would be almost 300.
Yeah.
There we go. All right, we're out of time. No new homework tonight, but plan on driving forward tomorrow. Thank you guys very much. It is going to be interesting if we have subs in here that are not math people. This is kind of high content level, so maybe I'll just leave a chalk talk or something. It's fine.
chalk talk.
A little video where you see what I write and hear what I say.
What do you say?
Words. Have a great day, guys.
Hey, 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 hey.
Do not be always wet.